Hi, in a previous video, we saw how we can use the idea of particular integrals and complementary functions to solve first-order differential equations. And we saw that to find the complementary function, we have to solve the first-order homogeneous differential equation. In this video, we are going to use the same ideas to solve second-order differential equations, but for this video we are only looking at homogeneous cases. Let us see how we can form a second-order differential equation. Let's consider this equation. Y equal a e raised to the power x minus 2 b e raised to the power negative 2x minus 1. We can find dy dx, and we'll see that dy dx is a e raised to the power x plus 4 b e raised to the power negative 2x. We can also find d squared y dx squared to get a e raised to the power x minus 8b e raised to the power negative 2x. From here, we can show that d squared y over dx squared plus dy dx minus 2y is equal to 2x minus 1. And this is just a second-order differential equation with constant terms or constant coefficients. What we began with is the general solution of this differential equation. This is the general solution of this differential equation. Differential equations of this form, a d squared y dx squared plus b dy dx plus cy equal f of x, are very important in the real world. The general solutions to these equations must contain two arbitrary constants. For this our case, we have the arbitrary constant a and the b. How can we solve second-order differential equations? Now we have seen that we can prove that this will give you this. Now, if you are given this one, how can you get to this point? How can you get the general solution? We concentrate on the equation with the homogeneous equation. Let's start with the homogeneous equation. In the next video in this series, we are going to look at the non-homogeneous case or the inhomogeneous case. But for now, let's just look at the homogeneous case. So we first let our y equal e raised to the power mx. Also, you could let y be equal to some a, some constant a, times e raised to the power mx. That will give you, and then when you differentiate y 2 times and substitute in this equation, then you should get this equation here. If you let y equal a e raised to the power this, then you should have a here as well, a here as well, and a here as well. Now, we can factor out the a e raised to the power mx, or if we only use e raised to the power mx, we can factor out e raised to the power mx. And we will have a quadratic term inside. Since e raised to the power mx, or a times e raised to the power mx, cannot be 0, this equation that we have here, this term will be 0, and that is what we call an auxiliary equation. So this will be an auxiliary equation to this differential equation, am squared plus bm plus c equals 0. Therefore, the solution to this differential equation will be a e raised to the power m1x plus b e raised to the power m2x, where m1 and m2 are the solutions to this auxiliary equation. Let's look at an example. Solve this differential equation 2d squared y on dx squared minus 5dy dx plus 2y equals 0. We first write down the auxiliary equation. Remember, you don't need to start by assuming let y equal a e raised to the power something. Just from here, you know that your m is going to be squared here, m will stay here, and there will be no m in this term. So you have 2m squared minus 5m plus 2 equals 0. That is your auxiliary equation. Solve the auxiliary equation to get m as a half and m as 2. Therefore, your solution to the differential equation will be a e raised to the power half m half x plus b e raised to the power 2x. Second example, if you want to solve 2d squared y dx squared minus 5dy dx equals 0, we write down our auxiliary equation. It's just 2m squared minus 5m equals 0. And then we solve the auxiliary equation to give us m equals 0 and m equals 5 and 2. So our general solution should be a e raised to the power 0x plus b e raised to the power 5 and 2x. E raised to the power 0x is 1. It's just e raised to the power 0, which is 1. So it will be a plus b e raised to the power 5 on 2x. Third example. We're asked to solve this differential equation d squared y on dx squared plus 6dy dx plus 9 equals 0. We write down the auxiliary equation m squared plus 6m plus 9 equals 0. I'm sorry. This is 9y. That's 9y. So we solve the auxiliary equation. We see that we get a repeated value for m equal -3 and m equal -3. We can write our general solution as a e raised to the power -3x plus b e raised to the power -3x. However, this can just be written as a plus b e raised to the power -3x, which is just some constant times e raised to the power -3x. So it means we have lost one solution. So if we have a repeated value for m, we state a linear function ax plus b times e raised to the power that value of m. Solve this differential equation. D squared y on dx squared plus 4y equals 0. We write down the auxiliary equation m squared plus 4 equals 0. M squared equals -4. So that gives you m as plus or minus 2i. So we have the solution to the auxiliary equation is a complex conjugate of an imaginary number. Complex conjugates of an imaginary number. So we can write our solution as a e raised to the power 2ix plus b e raised to the power -2ix. But from our idea of complex numbers, we know that e raised to the power ix is equal to cos x plus I sine x. So this e raised to the power 2ix is the same as cos 2x plus I sine 2x. And this e raised to the power negative 2ix is cosine of negative 2x, which is just cosine of negative 2x is just cos x, cosine of 2x. And sine of negative 2x is negative sine 2x, so it's cos 2x minus I sine 2x. And so when we add these two together, a times this, a times that plus b times that, we should get this. And now the cosine terms can come together. So you have a plus b times cos 2x, a plus b times cos 2x, plus a minus b times I sine 2x. This whole term here we can call it c, and this one here, a minus b times I, can be d. So it will be c cos 2x plus d sine 2x. So this is our general solution for the case in which you have imaginary numbers as the solution to your auxiliary equation. This is the last example. If we are asked to solve this equation, d squared y over dx squared minus 6 dy dx plus 13y equals 0, we can write down the auxiliary equation as m squared minus 6m plus 13 equals 0. And so we solve the auxiliary equation. We get m equal 3 plus 2i, or m equal 3 minus 2i. Now, we can write down our general solution as a e raised to the power 3 plus 2ix plus b e raised to the power 3 minus 2ix. And we can factor e raised to the power 3 because this part here, this is the same as a times e raised to the power 3x times e raised to the power 2ix plus b times e raised to the power 3x times e raised to the power negative 2ix. And so we can factor out the 3x. And then, again, we remember that this whole thing here is c cos 2x plus d sine 2x. So we'll have e raised to the power 3x c times c cos 2x plus d sine 2x. So, different types of auxiliary equations. This is a summary of what we have done in those 3 examples. If the solution to the auxiliary equation are real and distinct, then our solution will be of this form: a e raised to the power m1x plus b e raised to the power m2x. If the solutions are equal, if you have 2 repeated values, then you have a plus bx times e raised to the power mx. These are the 2 essential ones to remember. From these 2, from this one, we can always get this. And from this, we can also get this. But it will also be good to remember this format. However, if you don't remember, you can always substitute here and then simplify to get something like this. Okay, thank you.